The thermal flux of high-level nuclear waste to fracture a bitumen formation, to alter the chemical and or physical properties of the hydrocarbon material within the formation, to upgrade a portion of long-chain molecules within the formation to more valuable hydrocarbons in situ, and to produce a mixture of hydrocarbons, hydrogen, and other formation fluids from the formation. Lord Oxburgh, one of the world's leading geologists and former British chairman of Shell, has said of the nuclear-assisted hydrocarbon production method, "I have often myself wondered whether it would be feasible to harness the heat generated by sequestered nuclear materials. I suspect that the major problems might well be political rather than technological." What should be truly unpalatable politically to Albertans would be to see their resource go undeveloped, and although no one is currently calling for that, the nuclear industry is a stark lesson in what can happen to an industry that fails to confront its shortcomings. The problems of nuclear waste are heat, ionizing radiation, and radiolysis, which breaks down water into its ionic components and in turn can be corrosive to fuel bundles and their containers. These liabilities are all assets in terms of producing oil sands. Hydrogen released by the process of radiolysis and the heat generated by the waste within an oil sands formation will overturn the equilibrium of the system which holds the bitumen in place and contributes to the in situ cracking and mobilization of the resource. The flux of the ionizing radiation also fractures, upgrades a portion of the long-chain bitumen underground. Alberta's resource can be exploited in a similar fashion to the SAGD method, with nuclear waste substituting for the steam chamber. A SAGD schematic is virtually identical with a temperature distribution drawing of a Yucca Mountain repository, in which a so-called heat umbrella forms around the waste tunnel, preventing water from entering and corroding the waste packages. With SAGD, steam mobilizes the viscous bitumen, which radiates away from the heat source to a boundary between the steam chamber and the formation, and then the mobilized bitumen condensed steam drains by gravity down the periphery of the chamber to a producing well. Gravity drainage is a very slow process, so it is preferable to have as large a heat chamber as possible. The heat chamber is the area bounded by the interface between the unheated portion of the formation and that portion heated by steam, or in the case of nuclear-assisted hydrocarbon production, the area heated by the nuclear waste. In practice, SAGD well pairs are drilled horizontally, in parallel, and are vertically aligned with an injector well about 5 meters above a production well. The heat chamber gradually expands to about 30 meters high by 15 meters wide, and since the wells are about 1 kilometer in length, provide a chamber area of over 100,000 cubic meters, which in regions like Cold Lake produce drainage rates measured in hundreds of barrels a day. Bitumen has unprecedented capacity to sequester radionuclides, which was noted by a recent international study. Even the Canadian Nuclear Waste Management Organization notes bitumen with fillers is a suitable sealing material, so radionuclides placed within an oil sands formation are unlikely to migrate beyond the boundary of a heat chamber. What about radioactivity of the oil you get from the formation, you might reasonably ask? Here there is a common misconception between radioactive fallout and radiation. Radiation sickness occurs when high-energy radiation damages or destroys certain cells in the body. Regions of the body that most vulnerable to high-energy radiation are cells in the lining of the stomach and intestinal tract and the blood cell-producing cells of bone marrow. When radionuclides decay, they release their energy in the form of ionizing radiation, which includes alpha particles, beta particles, and gamma rays. Neutrons can also be released, but they are not ionizing per se. Instead, they interact with the protons in hydrogen in the manner as a billiard ball hitting another, sending it away with all of the energy of the first ball, and by this mechanism, fast protons are